Think of a busy Ugandan boda network. If a major route is blocked, deliveries stall, and everyone down the line feels the impact. An ecosystem works exactly the same way, but instead of packages, it delivers energy. This photograph shows a woman harvesting maize, the main ingredient for posho. Every calorie of energy in that crop, and in the meal you eat from it, can be traced straight back to a single source, the sun. This diagram shows a basic savanna food chain. Energy transfers from the sun to the savanna grass, which is eaten by a grasshopper, then a lizard, and finally a snake. Look closely at the arrows. A common mistake is drawing them pointing toward the animal being eaten. Instead, the arrow shows the path the energy takes, moving from the grass straight into the stomach of the grasshopper. A food chain is an absolute map of energy transfer. It traces exactly how solar power is converted into life-sustaining fuel, one organism at a time. This image shows the entrance to Queen Elizabeth National Park in Uganda. In a real habitat like this, animals rarely rely on one food source. This diagram represents a full savanna food web. It links multiple food chains together, mapping out how acacia trees, gazelles, and lions intersect in a working environment. We organize these organisms by their roles. At the base, we have producers, which make their own food. Above them are the primary consumers that eat the plants, followed by secondary and tertiary consumers hunting the layers below them. Let's trace a single path, grass to zebra to lion. While the lion is a secondary consumer, it sits at the third trophic level. You must count starting from the producer at level 1. Because an animal might eat multiple different things across the web, its consumer label can change. Counting up from the foundational energy source is the only reliable way to pinpoint its ecological rank. A savanna has millions of blades of grass, but only a handful of lions. This 3D pyramid shows the 10% rule in action. As energy moves up a trophic level, 90% of it is lost, burned off as heat, or used up through physical movement. Only a tenth of the original energy survives the jump to the next predator. Look at the sheer volume of the base compared to the tip. It takes massive fields of producers to sustain thousands of herbivores, just to provide enough residual energy for a few apex predators at the very top. Ecosystems run on strict physical limits. The rapid loss of thermal energy puts a hard mathematical cap on predator populations. This chart shows our original savanna food web. Let's introduce a disruption. Imagine a disease outbreak spreads rapidly through the herbivore population. The gazelle population crashes and is entirely removed from this system. Trace the arrows connected to the gazelle. Pause the video here and predict exactly what will happen to the lion population and to the savanna grass. Memorizing a food web isn't enough. You need to be able to accurately predict how interconnected networks react when put under sudden stress. Following the arrow upwards reveals the predator impact. Without gazelles to eat, a primary food source is gone. The lion population drops due to starvation. Tracing the arrow downwards shows the producer impact. Because the gazelles are no longer grazing, the savanna grass overgrows. That overgrowth creates a secondary ripple effect. Denser grass physically changes the landscape, forcing out ground-nesting birds and altering insect populations that rely on short vegetation. This table summarizes the core rules for analyzing any food web. Arrows track energy flow. Producers occupy level 1. 90% of energy is lost at each tier, and when tracing a removal, predators decrease while their food sources increase. Every species serves as a vital check and balance for the rest. Pull out just one thread, and the biological network shifts to compensate.